We've been talking about gas laws. We talked about the relationship between pressure and volume. And now we're going to talk about the relationship between volume and temperature of a gas. Here's a graph showing the volume of gas versus the temperature. So they took a sample of a gas and kept the amount of gas constant and kept the pressure constant and changed the temperature and looked at what happened with the volume. As we see, we get nice straight lines here. What's interesting about all these lines? It's down here. They all intersect, right? They all come together at the same point. When you have something like that happen, it's usually significant. So they've taken these different gases, helium, methane, water, hydrogen, and dinitrogen monoxide. And when they graph these, it all comes together down here. And they intersect at a temperature of minus 273. Now, these dotted lines especially show that they did not make measurements there, because when you get below 100 degrees Celsius, water is no longer a gas. And so they just extrapolated. They had data points here, and they just drew a straight line to extrapolate the data, but it all intersected here. So this is a significant temperature. When we draw a line on a graph, we can represent it mathematically. Do you remember what the equation for a line is? Y equals what? Mx plus b. Thank you. Okay, you got to dig deep. Back to math class. We haven't talked about this. So this is the equation for a line, where y is the y-axis. Here it's volume. And x is the x-axis. Here it's temperature in kelvins. And m is the slope of the line. And b would be the intercept, where it crosses 0. Well, it's a lot easier to graph something and to do calculations if the intercept is 0. And so this was the origin of the Kelvin temperature scale, because when we use the Kelvin scale, then the y-intercept is 0. And what that tells us is at 0 Kelvin, the volume is 0. So that's the origin of absolute 0 and the Kelvin temperature scale. So what Charles' law tells us is that volume and temperature are directly proportional. They're directly related. If one increases, the other increases. But what's really important is that we have to use the Kelvin temperature scale. This is the only quantity where the unit has to be a certain one. It will not work with degrees Celsius. Because when we use Kelvin, the equation for our line is volume equals B, the slope, times the temperature. And there's no plus anything. This is just a reminder of how we convert. We take the Celsius temperature and we add 273. And we call 0 Kelvin absolute 0. Looks like okay, doesn't it? It's a 0. So here is the mathematical expression of Charles' law. V1 over T1 equals V2 over T2. On the exam covering this material, on your table of useful information, I will give you these gas laws. So you don't need to try to remember those, but you need to know how to use them and how to choose the correct one. So let's do an example here. Suppose a balloon containing 1.3 liters of air at 24.7 degrees Celsius is placed into a beaker containing liquid nitrogen at minus 78.5 degrees Celsius. What will the volume of the sample of air become at constant pressure? Well, let's just think about what we expect to happen. If you take a balloon at room temperature and you put it into something that's really, really cold, liquid nitrogen is really cold, minus 78. Do we expect that balloon to get bigger or smaller? We expect it to get smaller. And that's what that graph would predict, right? If, oh, I missed, start down there. As the temperature decreases, the volume should also decrease. So when doing these gas law problems and we have all these numbers, we're going to use a table to help us organize all of our numbers. So we'll start a little table, and then after we've read the problem once, always read through it once, then go through and pick out the numbers. So there's 1.30 liters. So I'm going to write that in the first place here. Liter is a unit of what? Volume. Liters measure volume, and so this will be my volume column. And then the next number is 24.7 degrees Celsius. And degrees Celsius measures what? Temperature. Now this is where you can save yourself some grief. It has to be in Kelvin. All temperatures for gas laws have to be in Kelvin. They're usually going to give them to you in Celsius. I've never seen a thermometer that has kelvins on it. We measure the temperature in degrees Celsius. About the only time chemists use kelvins is for gas laws. And the conversion is easy. When you see a Celsius temperature, convert it right away. So right here on the spot, we're going to convert that to Kelvin. And that's going to be 297.7. Check my math on that. Or I'll check my math. You got to get your calculators out. We're going to use them. Yes, 297.7. So, balloon containing this much air at this temperature. Those numbers are related. They're together in the problem, and they need to be together on the table. And then it says it's placed into a beaker. So there's some words here that are telling us we're doing something. Something's changing. The stuff that comes after that is going to be condition 2. So this is condition 1, what happened the way it was initially, and here's number 2. Here now the temperature is minus 78.5. And again, we're going to see the degrees Celsius, and we're going to convert it to Kelvin right away. 194.6, thank you. Now I'm out of numbers, right? I wrote down all the numbers. I have an empty square in my table, and hopefully that'll correspond to the question they're asking. What will the volume become? So they're asking me for a volume, and I have a volume here. It's in row 2, so I'm going to call that V2. So up here I've got V1. This is V2. We don't know what it is. This is T1 and T2. And so when we go to the table of useful information on an exam and look for an equation, we're going to look for one that has T1, T2, V1, V2. And that will be the Charles law. Again, I don't expect you to memorize those. So what are we going to rearrange this equation and solve for?
Multiply the top and bottom by TT.
Yeah, we are going to multiply. We're going to do that. But let's first identify what letter are we trying to separate?
Oh, V2.
V2. So we're trying to get V2. Can you see that okay? We're trying to get V2 by itself. Now, some of you are real good at rearranging things, and you can do this without any help, so you can just ignore this part. But many of you, the algebra thing just really didn't work for you. It didn't make a lot of sense. So for those of you who don't like algebra, when we look at this equation, we see that there's fractions involved. We want to get rid of the fractions. We get rid of fractions by cross-multiplying. So cross-multiplying means that we're going to take the top of one side and multiply it by the bottom of the other side. So that gives us V1 T2. And that is equal to, let's use a different color here, the bottom of the first side and the top of the other side. It's cross-multiplying. So T1 and V2. And we have made the nasty fractions disappear. Any questions about cross-multiplying? We're going to be doing this a lot. So there's our V2 that we're still trying to find. To get him by himself, we have to get rid of the other things that are with him. So there's a T1 over here. To get rid of that, we're going to divide by T1. Because anything divided by itself is 1. T1 over T1 is 1. And now we've got V2 by himself. But we can't stop there, because these two things were equal. And we need them to stay equal. And so if we do something to one side, we have to do it to the other side. So if I divide one side by T1, I have to do the same for the other. Okay? Now I have my equation, but it's all kind of messy. So I'm going to copy it over. I'm going to say V2 equals V1 T2 over T1. And just be real careful. It's very easy to mix up the 1s and 2s. Some of you can look at the Charles law equation and rearrange it like this in your head. Great, you do that. Any questions about how I got the equation? We've done all the hard stuff now. We've got an equation that's set up to solve for what we need. We have everything labeled in our table. Now all we have to do is plug numbers in for these variables. V1 is 1.30 liters. And T2 is 194.6 Kelvin. And that's going to be divided by T1, which is 297.7 Kelvin. It takes part of a second longer to write the units in here. Just do it. Seriously. I'm getting text messages like, 12:30 last night from my students in Visalia. What's wrong? Why am I getting the wrong answer? They're doing the similar gas law stuff. I'm like, well, put your units in. Because she's solving for volume, but then she's converting liters to Kelvin by subtracting 273 at the end. It's like if you had units in there and saw that your answer had liters, I think maybe then you wouldn't be tempted to convert to Celsius. But there was no units anywhere in her work. Put the units in there. They are your friend, okay? You have to bring your friends along. Let's look at what the units are doing here. Here we've got a Kelvin and a Kelvin. My pointer's not working very well. So the units cancel out. The units act a lot like variables, right? A's and X's and stuff. They cancel out. What unit is left? Liter. Liter is a unit of volume. This is good. This is suggestive that we may have done this correctly. So now you do the math and get out your calculator and make sure that your calculator's cooperating. It's never your fault. It's the calculator's fault. But it's a shame to get this far and then have your calculator screw you up. So I'm going to record this answer with 3 sig figs. As we point 850. It was 84978 blah blah blah. That rounds up to 850 liters. before we started calculating, we predicted that the volume would go down. Did the volume go down? It did. So that's a good sign. The most common thing that happens, most common mistake, is that you'll get the temperatures upside down. If you get those upside down, then the change goes in the wrong direction. Any questions? Let's see what would happen if we did this with Celsius instead of Kelvin. So if we did that, we're going to have the same initial volume. And temperature 2 is minus 78.5. That negative sign is already a red flag. And then 24.7 degrees Celsius down there. And you look at the units and you say, oh, degrees Celsius, those cancel out. We're doing just fine. That whole Kelvin business was crazy. 1.3 times negative 78.5 divided by 24.7 gives us a volume of minus 4 liters. Is that the same as 0.85 liters? No. Can you have a negative volume? No. You can't. Celsius doesn't work in gas laws. There are lots of, I could prove to you mathematically why it is, but I'm guessing that you really don't care that much about that, so we will save my voice. Celsius doesn't work. It has to be in kelvins. Okay? Temperature in kelvins. Did you hear that? Okay? Because I tell students this, and then like the next day, they're doing it in Celsius. Like, oh, what's wrong? Is it in kelvins? No. It has to be in kelvins. Really? Yes. Really? Kelvins. Kelvin, Kelvin, Kelvin. Okay? Kelvin. The next law we'll look at is Avogadro's law, and maybe I should change sections here.